The work that Soham gave to me is on this spin system, the domain-size-dependent global spin exchange dynamics. It's a spin system that reduces energy by exchanging the spins of positions.
Dalia, before we
Yes.
start, can I suggest you something?
Yeah.
Instead of just directly going to the model and so on, just tell the motivation. Why we go for the exchange dynamics and all these things. From the persistence point of view. Or just give the background of the spin flip dynamics and then you go for the detail of what it is.
Well, in spin dynamics has been found a relation between a Markovian measure and a non-Markovian measure. And this system is interesting because it breaks the relation that has been found in many other systems, not only on just spin flip with nearest neighbors interaction far from equilibrium. And so it's why we started studying this system, even if his application is on social phenomena. It was inspired by the social segregation. And well, the content of this talk will be on our first paper. It's already on archive. We are fighting to put it in PRL. And plus other results that came from thinking on the questions of the referees. Now, the model we study is inspired on the Schelling model. This is a model made on the 1971. And what Schelling was trying to do was to study the social segregation that can be, you have sets of people, they can be differentiated by race, language, ideologies, and they feel more comfortable surrounded by people that are like them. And they discriminate the other type of people. So say that the people will segregate by their own decision is something like you need context, right? For example, if you have segregation because of the economy of the place, because of ideologies, then you need like context to say this segregation were caused by the decision of the individuals and not by external influences. And it's something that Sherin discussed, but even if he can apply his model. Now, he supposed his first approach to study the segregation is only with two types of persons. You have in your city people mix living in their houses, people of different races in the place, and they have certain amount of tolerance for saying I want like 50% of people around me be like me and 50 can be different, or it can change, less tolerance or more. And they interact with local neighborhood. It can be like one person on left, one person on right, two person on left, two person on right. And this is fixed over time. But they can move globally. They can go anywhere they want. And they move in between, in one lattice, it could be seen like you move in between two persons, or if you study this in 2 dimensions, you left empty houses and they go to empty houses. Now, this is very, very similar to a quenching dynamics under zero temperature for classical spin system, Ising spin system, where from infinite temperature you reduce the temperature of your bath to 0. This caused that from a random distribution of spins, you reach ordered spin of states all up or all down. Now we see an analogy with the Schelling model. We can see individuals as spins, where now we try to make like like a model more related to spin models that we know in physics, then we make the spins exchange. We also can study this system with vacancies, but it's like a work that we are still on it. Then here the spins exchange instead of going to an empty site and increase the happiness, moving the spins to a place where they will have lower energy is like the equivalence. Increase happiness, reduce energy. And well, sharing model consider nearest neighbors, and the model we study consider that spins interact with the nearest domains. This could be like this spin interact with all the spins that are aligned in the same direction on this side, and other spin aligned in the same direction on the other side. Questions?
I have a question, yes. So in this global spins change, you interchange two spins, right? But wouldn't the dynamics that you study are different if instead of that you just change the direction of one spin instead of interchanging positions?
Well, if you just flip spins,
Yes.
you will reach all spins up will be your direct state, or all spins down. But when you exchange spins of positions, your magnetization remains same during the wall dynamics, and you at the end have like two domains. This may be the first thing you can think, but there are another difference. The other is like when you are studying the growth of the domains, you with the spin flip only consider one spin, but now you have like to consider the other spin, and the spins usually exchange position when you have zero energy. This occur in the domain walls, so this will be seen later. Hence, now you will have like a condition probability to flip. You can see yes, like if both the spins were flipping, but now with the conditional probability that you select a spin that is in a domain wall. I don't know if this is clear now, but
Yeah, it is.
okay.
Another question. So your initial state have 50% of the spins down and 50 up.
Yes.
The dynamics are different if you do it different. For example, 20 up and 80 down.
I still don't try it, but I think you will reach equilibrium faster than.
No. The dynamics remain same. For spin flip, that's called exit probability. So if you have 60% up and 40% down, then the probability to go to all up state is 60, and probability to go to all down state is 60. So
the exchange dynamics.
No, I'm talking about spin flip first. So because I'm comparing with that. So all that things, those things will remain same. Okay. However, your speed of the dynamics also will remain same. Like it's 200 strict. Which we really do not know will change or not is the non-Markovian phenomena. So almost the standard Markovian phenomena remain similar. Domain growth, autocorrelation, and your exit probability.
So you will have faster, bigger domains because you have already a lot of spins in the same direction, but the velocity in what it evolves will be.
No, your domain
same?
growth exponent will remain same.
Yes, but the size of your domains will be.
It's still random. You're still starting with random. So.
But you have more in one direction.
Yes, but the only thing which initial domain size will be different for the reason that only thing is that what is the probability that two spin will be together. That probability that changes just.
Yes.
Because instead of 0.5 to the power 2, it is 0.6 to the power 2.
But if the spins are already together, as you don't have temperature, then.
Yeah, but your growth rate will be same. Your prefactor will be different. The constant in front will be different. That depends on your initial condition. Nothing else. Scaling remains same. So your speed remains same.
Just the speed remains same.
And hence the autocorrelation function. The rate of decay of the autocorrelation function remains same.
Well, why we studied this domain size dependent dynamics? Because, well, the purpose in the application is that this model could represent social segregation where individuals are under social pressure because they interact with world domains that put pressure on them to change to their opinion or to move from there in this case. And also we study in this system Markovian and non-Markovian measurement, and for this system are not related as we talked before. And when the system is self-organizing by itself, it has a transition into the nature of the evolution. So this is, I think, it's interesting. And how we model this domain size dependent dynamics, we have this Hamiltonian, and the index J is for the selected spin. We select this is the Hamiltonian for a single spin. So we select for the world configuration. Then J is the spin we are studying, and this is the neighborhood of the J spin. So I run over the nearest domains, and yes, this is clear. Okay. So we have the Hamiltonian for one configuration. Now we measure the change of energy caused by the spin exchange. This is basically measured the Hamiltonian for the spins just where they are, and we select the spins. We make like if we exchange them, and we measure the energy by the spin exchange. And so the difference between the energy of the spins, like if they exchange, and the energy where they are, is the change of energy. We use this algorithm that basically is like you have 50% of tolerance. So if the change of energy is lower than 0, then they exchange. If it is higher than 0, we don't do it. And if the change of energy is 0, they exchange with probability half. Now repeat this process n times. It's like a Monte Carlo time step. And I forgot to say
a trivial question, but nonetheless,
yes.
Shouldn't it be n half times? Because you're moving two spins.
No. Well, we tried this, and the results are like weird.
So it must be n times.
Yes.
Well, okay, should not just say that. There is a reason, because you are selecting n spins, right? So the basic condition is that you are basically selecting one spin, and then you are conditionally selecting another spin. So your number of update is basically still selecting one spin.
The changes to spin.
Yes, but once you select, and then what is the probability that you select another spin,
No,
given that first spin is selected?
Let me ask them this way. If it happens that these two spins are equal,
Yeah,
then you don't do anything.
We don't do
But
anything.
it counts, it's one of these n times, right?
Yes, but this doesn't. As you don't do anything, this won't affect your persistence. That's.
Yeah, but so,
But
so
it's
for
going as an
instance,
update.
if you have bad luck, then you do n times your selection and never do any movement
Yes.
during one Monte Carlo time step.
we study the fraction of domain walls. So between domains, we have like imaginary walls. Those are our domain walls. And this fraction of domain walls goes with time with exponent decay with exponent 1/z, where z is the domain growth or ordering exponent. So this exponent basically tells us how our system is reaching the order. And this is not the only way to obtain the domain growth exponent. You also can compute the the spin-spin correlation and measure his correlation length. This will give you also the domain growth exponent. Now we study persistence. This is the probability that a spin doesn't flip or doesn't make a spin exchange until certain time t. And this goes as a power law with exponent minus t. Basically, the persistence probability is the number of persistent sites over the size of the lattice. So, as we can see, once two spin exchange, the sites stop of the persistence and these remain forever. Hence, this is a Markovian measure, a non-Markovian measure. But for the fraction of domain walls, your actual configuration only depends on previous. Hence, domain walls are a Markovian measure. So the relation that previously has been found is that the correlation length for the persistent sites is like the correlation length for the spin lattices. Then have a relation between a non-Markovian measure and a Markovian measure is like something great, because then you don't need the wall history for having the information of the non-Markovian measure. And so here are our measurements. The main plot here shows domain wall versus time, the inset persistence versus time. So domain walls decay as a power law and then exponential because of our finite system sizes. And here is the final value that as we end with two domains, then it will be 2 over n, the value of these domain walls. And persistence decay as a power law, then it has a metastable state and then decays exponentially. This metastable state occur in the transition, like from having still an evolution of the system and having saturation. So have like a part of this metastable state is happening during the evolution of the domain sizes, and this is, and part of the metastable state is also when you already reached equilibrium. And what this happened because you have two domains, and the domains that are in the domain walls, they can keep exchanging positions with change of energies here. Well, we found that the persistence decay with exponent theta 0.445 and zeta is z is 2.47. Now, there is a way, indirect, you always get from indirect ways the correlation length for the persistent sites, and one is that the distances between the persistence probability has some information on the correlation length. Hence, so this distance is n at zeta theta, where zeta is the exponent of the correlation line for the persistent sites. Hence, if you search to collapse to join these curves, you can know the value of zeta. And you do this through this equation. And we found zeta equal to 1.2. That is different than Z. And it's 2.47. And this is like the first result that shows this.
Do you expect the zeta will be different before measuring?
That it will be different from the fractal point of view or from...
No, just go back. You have a value. You have a value of Z, right?
Yeah.
So
You went ahead.
From... sorry. From this relation.
go forward one step. You have a value of Z, right? And Z and theta. Before doing this second figure, will you expect that you get a zeta which will be different than Z?
I skipped this. So, when we previously saw fractals, then this condition is related with that the persistent sites are forming a fractal. And, well, basically this says that you cannot have a negative dimension. We see that with the value of Z we get from the domain walls. This condition is not fulfilled because we found Z theta equal approximately 1.09. But if in this case, if we use the zeta from the correlation length of the persistent sites, then we find something around 0.44. Then this fulfills the condition of having no negative fractal dimensions.
I think I'm confused with the symbols. So you have Z, you have theta, you have Z, thetas. This is Z times theta?
Yes.
Oh. And why? Why do you need it, or what does it mean?
So this condition should hold.
But what is it? Why? What is theta times?
So this comes from here, and it's the relation from the two-point correlation. But
where's theta times? Where's
so
Z times theta?
yes. So what everybody
why
says
play the
is
role?
that Z and theta should be equal. Z is the domain growth exponent from domain walls, and theta is the exponent of the correlation length for the persistent sets.
Exponent of the
Could you prove that?
correlation length.
Could you prove that? Why Z theta is equal to D minus B?
But from the two-point correlation,
This is a simple argument.
it's from the two-point correlation.
Yes, yes.
But well, I may see it more useful to prove
And
it
why you are expecting
after.
Z equal to zeta? That's the whole point. Or why people expect that so?
I need to see that slide. Okay, so the two-point correlation has two behaviors. One when it decays as a power law and when this saturates, because we have finite systems exist. It comes from the two-point correlation. I don't know if I should jump until there's something.
Just wanted to be reminded about the symbols, because I forgot what they mean.
So for now, I think we should take this like some equations that have to hold. If not, we have a negative dimension.
But D is
These,
topological dimension. So this is
It's
one.
the Euclidean dimension.
So it's one.
Yes,
Or it's 0.
it's one.
And df is the fractal dimension of the
Yes,
persistent sites.
yes. So theta later can be proved that is equal to alpha, where alpha is the exponent for the correlation length. So this is basically like the equation we saw before for the relation between the fractal dimension and the exponent for the correlation.
Okay.
This is this. And so
I think you
if,
should put these things on one slide so that one can compare. Because
or I can
otherwise
write
it's
this here
very
and remain.
complicated to keep track of what's the point in this
So
study.
if theta is smaller than 1,
Then D minus df is smaller than 1, right?
and suppose d is equal to
But that's
1,
okay.
so we put the there. No, something is wrong.
So C times theta must be smaller than 1.
Yeah, that's right. Df should be 1 minus r, right?
And that's what is violated.
Yeah, we wrote it right.
Yes. Yes, yes. Yes, if C, but of course bigger than 0.
You have C times theta larger than 1, and that's why it cannot be.
Yes, this is why we cannot take Z as
The basic argument is that it's a symmetric system, one dimension, so there must exist just only one length scale. Why the length scale should be different for measuring two different things. So if it exists just one length scale, one diverging length scale, then there exists only one exponent. And we already measured that exponent is Z, domain growth exponent, so that must hold for any kind of measurement. That's why people always took Z is equal to zeta. That was the argument to say that if I find out another diverging length scale, the exponent must be same. Which is validated here.
And we don't really understand why this, for instance, why the exponent of the correlation length is related in the way you say.
yeah. It's
I mean, this,
when I put the 2-point correlation, I can show this. Well, now we will continue with the evolution of the system. And well, in the regime when the domain was decaying as a power law, this is the like a typical change of energy when in this regime. So we have 2% of the exchanges are made with exchange of energy equals 0, and 98% with change of energy smaller than 0. So we almost have like a deterministic. Once you choose two spins that can exchange positions, they exchange. And we also measured the local energy. Okay. No, here we can explain. For the local energy, you just study for a selected site his Hamiltonian. And the change of energy of a single spin will be given like this spin is here, and then this spin is here. And we can see that when we study the local change of energy, we have exchanges even when the energy increases. So why this happened? Because it happening to when a spin goes to a place where his energy is even lower than where it is already. Like this spin is supported by 3 spin down. Very simple. By 3 spin down, and here will be supported by 4 spins down. So how do you remember the example?
You're trying to find out the increasing energy one.
Yeah. So here, I guess my energy is negative. My change of energy, my global. Because here this is completely unhappy, so it's like, yeah. It's like selecting,
And this energy increase only happens for the domain size dependent dynamics. So you should take the larger sizes. Simply is that in one case you have large domain size, sandwich between two large. Another case is sandwich between less. So total energy can decrease, but you can one side to increase. It's just because of the domain difference of the domain size in two different sides.
Because this has to be different. This has energy -2 and +2, and this has energy. So I think I should not do it. But the point is that there can be situations where a spin have already negative energy, but go to a place where it has even more negative energy. So the spin that here was unhappy, in the other place will be less unhappy. And well, at the ordered state, we, as I said before, we over with 2 domains. Then the spins located in the domain walls share the same neighborhood, because this spin interacts without this and without this. Then if this spin is here and interact with the same spins, then if this is here and at inverse. Hence, when at this ordered state, the spins exchange positions and are persistent, keep decreasing even if the system is in an ordered state. So here we show the results for when at the change of energy, global exchange of energy equals 0, spin exchanges definitely. Or when the change of energy is equal 0, spin doesn't exchange definitely. And the results are the same because most of our spin exchange are given by the decrease of energy. And yes, set, zeta, and the persistent exponent are C.
So that means that it doesn't matter what do you do when the energy doesn't change, the results are the same.
When the change of energy is equal to 0, during the disordered state, before you reach the ordered state, doesn't matter. Once you reach the ordered state, all the spin exchanges are given with change of energy equals 0. Then you just will see like the saturation of the persistence, but you won't see it going to 0 in those cases. Now, we study how is this transition. For this, we make collapse, like to see what is these distances, to try to find like another scaling length. And basically, as the domain walls are exchanging with probability half, we see that this is like a random walker with the condition probability of selecting another spin. So at the end, this gives you set equal to 3, more or less. Now we will go to fractals. We use the mass definition, and so our mass scales with the length of our fractal at power beta, where beta is lower than the Euclidean dimension.
What's the mass in the Cantor set?
Get the points?
What is it? I mean, how do you count the mass in the Cantor set? Okay.
That's when we count.
How do you define the mass?
But like a set of points, the mass of the set of points.
You cannot count the points, right?
You cannot count them, but they are there. So
Okay.
you
have the interval, right? The full interval from 0 to 1. Then the mass is what?
So
It's not the fractal, the interval from 0 to 1. But what is the mass of this? 1?
no.
So when the mass definition is valid?
No, what is the mass?
Yeah, that's exactly the question. When the
it?
mass definition is valid, mass definition is not valid in that sense.
This is not my question. My question is, how do you define mass? What is your definition of mass?
So somehow it's related with the amount of points you have there, yes?
Yeah.
But that makes no sense, because in the interval from 0 to 1, there are uncountable many points.
That's exactly the point.
So
the mass definition is only valid, is not valid for uncountable sets.
Even if the set is countable, then if you say it's the number of points, then it would be infinite.
But you cannot have an amount that is uncountable?
It depends on what you define mass. This is my question.
The mass, that's
So
exactly
how do you define the mass?
the mass definition is only valid if you have a countable set.
Countable set.
Yes.
And then what is the mass?
So the mass of the point. So for example, if you have a
What is the
pure
mass
Cantor
of the
set,
point?
each point have a unique mass. If you have a multi-Cantor set, then each point can have 2 different masses.
If each point has unique mass, then even a countable but infinite set has infinite mass.
Yes, the mass. That's how the mass diverges for L. ML diverges as x to the power beta.
Even if L is equal to 1, it's diverged. It's infinite. There are an infinite number of points in that interval.
If you have a continuous space, yes, but you are
No,
not
even if it is discrete. I mean, say the number of rational numbers. Say the rational numbers between 0 or 1 and 1.
But it have to be
What would be the
countable.
mass?
So it's a finite
Yes, they are
countable
countable.
number.
No. Countable and finite is not the same.
Okay.
So if they are countable, then the mass would be infinite. And
Yes, then you're
if
scaling.
they are finite, okay, then you have finite number of points, but there are no fractals with a finite number of points, right?
No, why?
Why?
This dimension is basically
If
the
a
box
set-
counting dimension. Your dimension beta, the fractal dimension, that's basically your box counting dimension, to be clear.
Beta is the box counting dimension.
Yes.
Beta. So
Beta
M
is the
should
box
be,
counting dimension.
then M is not the mass, it's something else. I don't know.
No, you can do the box. Okay.
You should not call it mass, maybe.
No, that's exactly the mass definition.
So please define mass. Then.
So if you have a finite countable numbers, but if you have a finite space, your numbers are your Cantor says this Cantor task numbers are finite.
No, they are not
Or-
finite. I mean, how do you say they are finite? They are not finite. They are infinite.
But how do you do the box counting measure in general then?
You take an interval of some size epsilon, and then you have a finite number of boxes,
Okay.
and then you can say how many of these boxes contain the Cantor points from the Cantor set,
Okay.
and how many, and this is your number n, right? The number of boxes, which depends on epsilon.
And how do you find out the dimension? The number of
Then
boxes.
you consider this n of epsilon. As epsilon goes to 0, you take the logarithm.
Okay. Now for the mass definition is exactly like that. If you find out which are the non-empty boxes, and now each point you define a unit mass. Okay.
That
So
doesn't work, right? Because in every non-empty box there are infinite many points.
that's exactly what I'm saying. There are a finite number
No,
of.
they are infinite. So you take one box, and you find a box which has at least one point of the Cantor set.
Mhm.
Then it has infinite many points of the Cantor set.
I don't get it.
Because
Because the definition
when
of the
you are
box counting
dividing-
is that the box should contain at least one point. So there is a finite measurable number.
But if it contains infinite points, then it still contains at least one point.
If
If it contains infinite many points, then it's still true that at least it contains one point. So any box of this, if you do the box counting method, any box contains an infinite number of points from your Cantor set.
No, that's not how you practically define the mass measure.
But it's what happens.
No.
There
So
will
then-
be places where you have nothing.
I mean, why do you like, okay, maybe this is an easier question. Why do you like to put this equation if you don't know what mass is? Why don't you use the box counting equation?
Because if you
Then
go
we
for the
would not-
multifractal mass, you have to elevate the mass with your value q. So you actually have to define the mass properly. And that the
Yes,
definition,
okay. So please define it properly.
that's exactly the point. So you have to have a countable finite set where your one box can so the way you are defining it, so each time I have a non-empty box, that box contains infinite number of points.
Infinite.
Infinite number. That's the way you are defining the box counting.
No, but it just happens. Okay, maybe
That's
let's postpone this discussion.
But you can define the box counting in a way so that each box define finite number of points, and then your mass would be different. And where your each unit as discrete, and you define an unit mass to that each discrete point.
Okay. I'm sorry. I mean, if we want to keep the shadow, then we should in fact stop here.
Sure.
and continue with the high one.
So we measure the box counting.
So how much time would you need? Because time is running out.
So I can just show results of box counting again. So the other results are like the distribution of the distances.
Could you show the results of the box counting?
Yeah.
Just results of the box count for this debate. Explain that figure, that's it.
Okay. Well, this is the typical
Box count.
definition of box counting. A number of boxes with objects inside and persistent size inside in this case, and the length of the boxes.
And for the main plot, that's the mass measure.
And the main plot is
Explain
the
that.
average, but it's basically the inverse of this one.
You are confusing again. You're
So,
confusing people.
Is it total
Define
number?
the main plot how it is.
What is
That's
this
it.
capital N?
Yes, exactly. Just define that. If you say it's the same thing, then Thomas's point is absolutely valid.
So it's the average number of boxes with persistent sites inside after discarding the empty boxes.
Which of any of the two, say in the nominator or the in the numerator or the denominator, is NT of S? So I thought that the number of boxes with
Yes.
some persistent site inside, this would be this little n sub t, right, of S. And the number of
This empty is basically okay. This
Okay.
empty is basically average number of persistent sites inside a box and inside a non-empty box.
NT.
Empty.
No,
M. This
Yes.
mass.
Okay.
Average number of persistent sites inside a non-empty box. Now that's exactly the mass measure. Like you imagine that each persistent site have an unit mass, small m.
Okay.
Now you given a box size, what is the average mass inside the non-empty boxes? So that's why for defining the mass measure, your space need to be discrete. Your number set should be countable and finite. Then only you can define the mass measure.
And then you don't have a fractal. But that's okay.
No, that's exactly the same thing as the box count.
Okay, no, okay. No, now I understand. I understand the mass measure for your fractal.
No, that's the standard mass measure.
But I don't understand the mass measure for the what it would be for the Cantor set. But, yeah, I mean, I think this should be discussed another time.
We measured the distribution of the distances between persistent sites. This is for times where persistence is decaying as a polar, and here when it is saturated. So here we see this because large domains are still not formed. So this like is cut. And we find like further dimension 0.67.
Dalia, what's the problem?
Is the fractal dimension plus 1.
Yeah, but
And df, the
it's
fractal dimension,
1.67
0.67.
plus 1.
Plus minus 0. Sorry, see, yes, here. See, yes.
So that follows a Levy distribution.
Yes.
It's not normal.
And well, we take the two-point correlation, but this is more complicated.
Yeah, maybe let's stop here. So.
Yes, because we found some issues. Then better stop here.
Thank you.
Thank you.